Now you are sitting in a technical interview, let us say, and you have been given to solve this series in the simplest way possible. So you'll obviously opt the most popular method, which is recursion. So let us say that it is, we declare a function and we follow the most conventional and broadly famous method to solve this, and we'll say that this is the most easiest and the most conventional method to calculate this series. However, what if I tell you that this is, though the most conventional method, it is not very convenient when it comes to solving for functions where n has a really great value. And today we are going to discuss about the disadvantages of this recursive function and the possible alternatives. So first of all, let us see how do the most crammed method, how does this come into existence, and we'll use a mathematical function fn to find it. Let us say we have f3, and we know that in Fibonacci series we have sum of previous two digits which give the third digit or the number, like 1 and 2 will add up and give 3, 3 and 5 will add up and give 8. So for f3 we'll have 1 plus 2, that is f3 minus 1, 3 minus 2 plus f3 minus 1. So for our convenience, let us say that this is wrong actually. This has to be, this has to be fn minus 1 plus fib n minus 2, which is equally not easy or equally not beneficial, right? Equally disadvantageous. So for f3 we calculate it in this way. For f4, if we follow this same convention, we have f4 minus 2 and f4 minus 1, that is 2, and here we get 3, that is 5. So we get the first 4 digits, 1 2 3, 1 2 3 4, and this is the fifth one that we get. So this exact function that we are getting is actually can be generalized into fn minus 2 plus fn minus 1, and it can be verified. So we use recursion function to calculate all of this, and if f is 0 or f is equal to 1, we have the value equal to 1, because we obviously cannot subtract the previous values. So let us analyze the time complexity of this famous recursive function. Now for this given function, let us say we calculate the time complexity by tn function, and obviously first of all we have the function called twice. So here also we'll write tn minus 1 plus tn minus 2, and additionally we'll have these assignment operators which contribute plus 1 over here. So we have this plus 1, this minus sign will give 2, this will give 3, and this will give 4. So we have this time complexity in this manner. Now we know that t0 and t1 will be equal to 1 as discussed earlier, and for t0, like n will be equal to 1 or n will be equal to 2. Now let us make one assumption that n tn minus 1 is equal to 2 tn minus 2. Now for very large values actually this will obviously be be equal. So modifying Tn, we are going to get, since you have assumed that both of them are nearly equal, 2Tn minus 1 plus 1 constant C. Now we can also write it as 4T n minus 3 n minus 2 plus 3C. Going to generalize this equation and keep assuming till we get a generalized thing to make an assumption again, or to deduce an observation from all this. So I'm going to go further with 8T, and here I do minus 3. So we have a loss of 4 here, so I'm going to add, which gives 7C. Similarly for 16T, n minus 4, and here we get a difference of 8. So I'm going to add it over here. So here we get a pattern, that is, this is for the first, this is for the second, this is for the third, and this is for the fourth. So let us say that we get a pattern that is 2k, 2 to the power k, t, n minus k, like from 1, 2, 3, 4, and plus there's a constant, so 2k minus 1 into the constant. I'm running out of space, I'm going to erase it a bit. So we get this generalized equation over here, and for this equation, let us say now if we want to find T0, here obviously we'll have for T0 n is equal to k. So we can assume that Tn is directly proportional to 2 to the power n, and which gives our big O 2 to the power n, which takes a lot of time when n is very high, and probably the worst case that we know. So this recursion fails to fulfill our simplest and the fastest way to calculate the Fibonacci series. So we need to find out a proper solution, let us say, and we'll make use of the recursion tree to calculate this exact thing. First of all, let us analyze the recursion function, and we should know that we form an implicit stack whenever we have recursion. For example, if I have to calculate for f5, first I'll go to f4, and this f5, it is pushed into an implicit stack and placed here, let us say. So f4 will go to f3, and here again it is pushed into this implicit stack f4, and similarly f3 will go to f2, so it will be pushed, f2 will go to f1 and it will be pushed, and f1 will go to f0, and f0 will remain. So here on top we'll have f1, right, and the sequence of operations will happen this way. Now to find out the recursion tree, I'm going to erase it and make it in such a form that it is easier to accommodate as many functions as possible. Let us find the recursion tree from here. So we have f5 going to till f0 as discussed, and it forms an implicit stack. So f5 will call f3 also, like sum of these two will give birth to this. So f3 will also call its two functions, f2 and f1. Similarly with f4, f3 and f2, and similarly with f3, f2 and f1, and for f2, f1 and f0. f0 doesn't call, but this is what. Now we see a repetition of all these functions a number of times, here, 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 and that's why the delay comes and the time complexity becomes O2 to the power n. So we need to find a method in which whenever we come across one function, and if it is in the memory, we are not going to calculate it, or we are not going to return it. So this process is called function recursion with memoization, and we'll write a simple program to implement it. Now the simplest way to do is finding an array, let us say fn, and storing the elements into it, and let us find out how. Now first of all I'm going to declare an array, let us say f, and its limit, let us say if we have to find the Fibonacci series for n elements, we are going to set the limit for n by 2 plus 1 elements. So if we have 100, we are going to find for 51 elements. And then I'm going to set a loop, let us say for loop, in the main function. We have not started our Fibonacci function yet, and we have the limits, and here we are going to set fi is equal to -1, and it is getting stored in the memory. And now when we have our function, so first of all we find out that if n is less than or equal to 1, return 1, else, now else what are we going to do? Fn, and let us rather set an else if function and say that else if fn is not equal to -1, that is, if it is -1 it is already in the memory, and if it is not equal to -1 then we are going to return it with the help of a recursive function. And then we are going to, let us say, return fn. So what did we do? First of all we set the memory, and we set fi is equal to -1, and it means that it is in the memory, and whenever we find out that it is not in the memory, then only we are going to return it. Unnecessarily every time we are not going to return it. So this is our simplest way and the fastest way to actually find out the Fibonacci series. And this assignment operator, it also takes one extra space in the time complexity, so it can also be removed if in the main function only we declare that f0 is equal to 1 and f1 is equal to 0. So it will be out of this function, so the time complexity will further reduce. So I hope you understood. I'm going to show you this view of the entire function, which is this, and it is very simple, and I hope you understood. You can verify it in your laptops.